once we get all that information, then we can understand how reflexes work, reflex pathways. In lab, we're going to look at the histology of different types of neurons. Neurons have different shapes. These are different shaped neurons. Neurons have different specialized components. Oops. Just like muscle fibers have different specialized components, we'll see how neurons have different specialized things. Okay, so how do reflexes work? You all know the knee-jerk reflex. You know that when you hit it, you kick your leg up. So we want to understand how they work, which means to understand how they work, we need to know how neurons work. In order to know how neurons work, we can also figure out, well, once we figure out how neurons work, we can also figure out what happens when things don't go right here. What happens if there is a blockage of a receptor, or if there's a cut nerve, what kind of things could we expect? Our nervous system topic encompasses a lot. This is just the start. We're studying nervous tissue today. We're going to learn about the brain. We're going to learn about cranial nerves, spinal cord, spinal nerves, peripheral nervous system, autonomic nervous system. There's a lot in this that let's learn about the nervous system. So we're going to start today. One way we can divide up the nervous system is central versus peripheral. Central meaning at the center of everything, because this is where all the information goes to and all the information leaves from. It's like your major station. All things go in and out of it. Central nervous system. When we say central nervous system, the obvious one is the brain, but your spinal cord is also a major hub. It also does, we traditionally think of our brain as a place where we think, where we process information. I wouldn't say that we think with our spinal cord, but we definitely process information with our spinal cord. The spinal cord is also crucial for that. Like to kick your leg up in that knee-jerk reflex, you don't need your brain. You know that you've been hit, but you don't need your brain to do that. So the spinal cord is also a really important part of the central nervous system. Anything else outside of the brain or spinal cord, anything else is considered peripheral on the outside. I'll write that out in a second. I'm going to write it twice here, and it'll make sense in a second when I write it twice. So anything outside of the brain or spinal cord is considered peripheral. That's one way you can divide it up, just simply based on location, and we'll see about the function in a minute. All right. Here's a huge map showing the basic divisions of the nervous system. You can see the brain and spinal cord are represented here, so this is central nervous system, and anything on the outside is peripheral. The nervous system is a control system. It tells our body what to do. In order to tell our body what to do, it also needs to receive information on what's going on in our body. Like there's a thermostat somewhere here that doesn't work that well in this room, which senses the temperature and then decides maybe I should make it warmer, maybe I should make it colder. So there's a decision-making thing. This is the decision-making thing. It has to receive information from the peripheral nervous system. You have to get input. And you have to do something with that information. You can send output. Also, again, if it's on the outside of the central nervous system, it's peripheral. So the common theme that we're always going to see here in the nervous system is that there's input. We sense something. We take that information and we decide what to do with it. That's what I mean by integration. We take that information and decide what to do with it. Once we decide what to do, we're always making decisions. We either do something or don't do something. Not doing something is a decision. So that decision, that's our output. to regulate what's going on in our bodies, we have to decide what to do, change something or not change something. There's a lot going on here. I'm going to break it down piece by piece. There is a part here that we're not going to discuss yet. We'll discuss it when we get to the digestive chapter. It's the nervous system of your digestive tract. We'll get to that later. All right, focusing on this part here, focusing on the input. That's known, excuse me, that's known as your afferent with an A. It's known as your afferent division. In your afferent division, this is where you have receptors of different kinds. I've listed a whole bunch here. I'm not going to expect you to know all of them right now. We'll go over them piece by piece when we get to them, but we sense a million different things. I kind of get annoyed when people say we have 5 senses, because we don't have 5 senses. You've got like 20 or something like that. So it's a really high amount. And in terms of conscious, if we mean conscious sensing, then we have vision, touch, taste, smell, hearing, vestibular sense. At least 6 conscious things that we can detect. And then even touch can be divided into light touch, soft touch, right? So that's light touch, high pressure, vibration, flutter. We learned all about all those different receptors in our skin. So we've gone over a bunch of these somatic sensory receptors. We'll be learning soon about things that we use to smell, taste, hear, see, balance. And then also, there are tons of things that we monitor without even thinking. We monitor how much oxygen and carbon dioxide and acid there is in our blood. We monitor oxygen levels in our lungs. We measure the stretch of our stomachs. And we don't think about it because it's automatically regulated. So that's what a visceral sensory receptor would do. Regardless of what it is you're detecting, they all follow the same basic pattern. You have a neuron of some kind. Here's its cell body. When I draw this open caret, this means the receiving end. So this is the receptor. If you remember, we talked about like Pisidian and Meissner's corpuscles. Those were nerve endings with connective tissue wrapped around it. This is the nerve ending that I'm talking about. So if this were a Pisidian corpuscle, I would draw that connective tissue surrounding it. To activate this receptor, there has to be some kind of stimulus. It could be something chemical, it could be light, it could be some vibration, touch, stretch. Tons of things can be stimuli. We have to detect something. A thermostat works by detecting temperature. It has a built-in thermometer. So we need to somehow detect the information, activate that sensory neuron, the receptor, and then send that information to the central nervous system. This extension that's leading to the central nervous system, that is our afferent. This is an afferent pathway. So this open caret thing, I'm representing as our receiving end. Can anyone guess what this is? We've learned this term. Axon terminal. This is the axon terminal. Which leads, in this case, it leads to the central nervous system. We're talking about this sensory. Once we get that information to the spinal cord, there's going to be a ton of other neurons here. For simplicity, I'm just going to draw one, because it will get pretty crazy. So I'm going to draw another neuron here, same pattern that I did here. Open caret for the receiving end. We'll get to the name of it coming up, what this thing is called. Here's the cell body. And then it'll communicate to something else. So it could be one neuron, it could be a ton of neurons. Just again, for simplicity, I'm just drawing one. It could be one neuron talking to another, talking to another, talking to another. The whole pathway. Brain and spinal cord receive information from the sensory neurons, send information out to efferent with an E neurons. Yes? Are neurons all the same length? Are they different lengths? Are neurons all the same length, or are they different lengths? They vary greatly. Some are really, really short. Some can be as long as a meter. They vary greatly in length. We need our central nervous system, both brain and spinal cord, for processing reflexes, all kinds of reflexes. And then our brain can do some great things that we're not going to talk about too much because that's a much bigger scale. And if you're interested, I encourage you to take more neuro classes when you can. Things like intelligence, memory, learning, emotion. We're just going to learn about the basics of what the brain can do. It's a mess.
Did anyone not put their name on the mini quiz? 'Cause
Okay. So the afferent with an A, that's the sensory side. You're sending an afferent signal to the central nervous system. If you want to send an output signal away from the central nervous system, that's an efferent with an E. Or if you want to pronounce it efferent so you don't mess it up. Again, same thing that I've been doing. Open caret, cell body, and a signal to somewhere else. Let's say this is a motor neuron. What would be over here? Muscle. So I'll just, for an example, I'll draw skeletal muscle. So this would be a neuromuscular junction. It could be a muscle, could be an endocrine gland, it could be a bunch of different things. We'll get to what it could be. But something over here, that we'll just call this our target or effector, the thing that we're changing. That's what an effector is, the thing that we're changing. So extending from the central nervous system outwards, that's the efferent with an E pathway. We're going to our target cell or organ, whatever that is. Something that we're controlling. It could be our heart, it could be our lungs, it could be our muscles, it could be a gland, it could be our reproductive system. Tons of different things we can control with our nervous system. Helps regulate most things in our body, not everything. Helps regulate most things. One way to help you remember this. This afferent neuron, the sensory neuron, it's approaching. Afferent is approaching the central nervous system. While efferent's exiting the central nervous system. Approaching, exiting. So you can see that it gets pretty complicated here. There's this branch called autonomic, there's this branch called somatic motor. Let's take a closer look at that. What do we mean by this? We've kind of covered this a little bit. The somatic motor nervous system. Somatic motor, soma means body. So just means controlling the body. Motor, or controlling the movement of the body. Controlling your skeletal muscles. Somatic motor neurons control skeletal muscles. And for the most part, this is conscious control. Remember the diaphragm on most of your days in this section. So if we follow this pathway and it's a somatic motor neuron, it'll lead to contraction. The tissue is a muscle, and you get contraction, you get a response. The other branch here is the autonomic nervous system. And as the name implies, it's automatic. Autonomic we don't think about, it's automatic. And the autonomic nervous system itself can be divided into two branches, the sympathetic and the parasympathetic. Sympathetic and parasympathetic. So skeletal muscle, that's somatic motor nervous system. Things like your smooth muscle, cardiac muscle, glands, that's parasympathetic. So pretty much everything else, other than skeletal muscle, is parasympathetic. The difference between sympathetic and parasympathetic, sympathetic is your fight or flight response. It's when you are in a situation that elevates your heart rate, dilates your pupils, stops your digestion. When your body needs to be at high alert. Could be like if you're running away from a predator, you don't want to get eaten. Could be you're trying to ask your crush out. Anything that elevates your heart rate to a significant amount, that's a fight or flight response. Parasympathetic, that's doing the opposite. It's your rest and digest response. You're getting your body back to baseline, getting your body relaxed, you're increasing digestion. So in other words, there's different focuses. The focus here is getting your muscles and blood and circulatory system ready to do something active. This is getting your body rested, but also increasing activity of digestive system. So think increased digestive system, increase circulatory muscle activity. The way I remember this, parasympathetic, think like paramedics. Paramedics help you get back to normal. This is your getting back to normal. Questions? So those are the basic divisions, and we're going to look at every single part that I just mentioned as we go through the next few weeks, because this covers a few weeks. Before we can do that, we need to know what are the major cells we find in the nervous system. And the major cells that we find, by major I mean the functionally important ones, they're called neurons. You might see them called nerve cells. This sounds awkward to me. Neurons is a much cooler word. Neurons, those are the specialized cells of the nervous system, just like muscle fibers are the specialized cell of the muscular system. What's special about these is that they can send electrical impulses within themselves. I think we have a misconception that the way neurons communicate is electricity from one neuron to another. It's not. It's usually not the case. It's that within one neuron, electricity flows through it, and then to communicate with the next neuron, it's mostly chemical, just like we saw with that neuromuscular junction. So it's electrical within the neuron, and then most likely it's chemical to the next. Electrical, chemical, electrical, chemical. It's just this domino effect. So muscle fibers also have electricity pass through them, so that in that case they have something similar. Another similarity, they have a long lifespan. Most don't undergo mitosis, which is why it's a bad thing if you damage your neurons. If you have nerve damage, we don't really have the capacity yet. Hopefully someday we can figure it out, but we don't know how to regenerate those damaged neurons. They also use a lot of energy. That's what I mean by metabolic rate. Thinking takes energy. Processing things takes energy. So what do you think they have a lot of? What organelle? Lots of mitochondria. Okay. I guess I'll just use the picture that I have up here already and take advantage of that. Let's use this one. So here's a neuron. Here's my rough schematic of a neuron. Like any other cell, so don't forget what we learned about cell structure. Like any other cell, it has a nucleus. See the nucleus here. Here's the main cell body. It has a plasma membrane, but clearly it has some really special, specific features. The part here that detects information, those are called dendrites. So these are called dendrites. What I've drawn here is this carrot. Dendrites are what receive information. In some cases, the dendrites can act as the receptor. In some cases, they're just receiving information from another cell. Either way, dendrites are receiving information. Dendrites detect. Dendrites detect. They're going to have membrane proteins on this surface here. We have membrane proteins in this region that receive information. Just like the motor end plate has receptors. This dendritic area has receptors. The word dendrite means like branched, so it's a pretty branched structure. Yes?
Did you say that a dendrite could be either a detector or a receptor?
When I use the word receptor, like a sensory receptor, what do I mean by that? I mean like it's detecting a stimulus like light or sound or something. But there's going to be dendrites on that end. There's also going to be dendrites over here and over here. Every neuron has to have dendrites to receive information. You got your dendrites, which detect. You got your cell body, which integrates that information. And then at the output, you know these terms already. You've got your axon and axon terminal. Even on a cellular level, we're following the same pattern. At a body level, we had input, integration in the central nervous system, output. Even within a single neuron, you have input on the dendrite, integration in the cell body, output in the axon terminal. It follows the same pattern. Neurons have to decide if they're going to be activated. I'll use an analogy later, like if you play that game, like the strong person game, when you go to a carnival, you hit the thing with a hammer. You can hit it as many times as you want, but you don't win until you hit it hard enough that it hits the bell. So this neuron can only be activated if it's hit hard enough, so to speak. We'll get to that later. One other language thing, one other terminology thing here. If you're referring to a cell, a single cell, that's a neuron. A a nerve is something different. It refers to something different. A nerve is actually, if you have a bunch of these axons bundled together, that's what a nerve is. It's a lot of axons bundled together. It's not referring to the cell bodies, it's referring to the axons. That's what a nerve is. So if you pinch a nerve, that means you're damaging axons, which means those neurons can't be activated as easily. Or they're activated too much. Yes?
So does that mean that there's a bunch of axon in that myelin sheath?
Does that mean there's a bunch of axons in the myelin sheath? We'll get to what the myelin sheath is later, but the myelin sheath covers individual axons. Myelin sheath covers individual axons. So a nerve likely has lots of myelin sheaths in it. What do neurons communicate with? We've already seen how neurons can communicate with muscle. It could be smooth, could be skeletal, it could be cardiac. Still muscle. So you call that a neuromuscular junction. Neurons can also communicate with other neurons. We see this here. Neuron to neuron, neuron to neuron. So this is just called a synapse with another neuron. I could call it like a neuron to, I don't know. Neurons can communicate with other neurons. Neurons can communicate with muscles. Neurons can communicate with glands. They communicate to many different types of cells. What's common between all of them, what we can call this connection, this region, this whole region between axon terminal of one neuron to the dendrite of another, that's known as a synapse. So a neuromuscular junction is a special kind of synapse. It's a synapse between a neuron and a muscle. You can just call it a synapse in general and you'd be correct. It's a synapse between the axon terminal of this neuron and the dendrites of this neuron. Synapse. You remember the space between two cells, like this space here is a synaptic cleft? That's where that term is coming from. So synapse in the little space between is the cleft. Synaptic cleft. Okay. So we normally think of neurons as a major thing that we see in the nervous system, but it's actually not the most abundant. Neurons are the most interesting. They have electricity flowing through them. They do cool things. We can modify them, drugs and stuff. But glial cells are the most predominant. Think of them as the support staff. They're the glue. Literally, glia means glue. In German or something. Glial cells support and protect neurons in many different ways. So in this crazy drawing here, in blue, here's the cell body of a neuron, here's the axon hiding under here, here are the dendrites of a neuron. Everything in yellow, everything drawn here in yellow, those are different glial cells. It looks pretty crazy here. We're going to go over each one of these different types and what they do. In an actual micrograph, neurons are pretty large. Here's the cell body of a neuron. All these other nuclei that you see surrounding this major cell body, all these other nuclei you see are glial cells. Those are nuclei of glial cells. All right, so what are the different glial cell types? The glial cells that exist in the peripheral nervous system differ from the ones that exist in the central nervous system. So let's go over peripheral first. Often, not always, but often, the axons of neurons are covered with a special sheath called a myelin sheath. So I'll try to draw like this. The axons are covered and wrapped around the cell. That cell is called a Schwann cell. Schwann cells, if this is the axon of a neuron, the Schwann cells are just wrapping around a bunch of times different segments along the axon, wrapping around it. Yes.
Are you able to see those wrappings on, if we were to look at it under a
Are you able to see those wrappings under a microscope? You will, yes. If you look at it in cross section, here it is in cross section. So this center dot is the axon. All this white space is the myelin. So this is in cross section. We can also see it in longitudinal section, and we'll. I don't know if I have it here.
What about?
We have a really good slide in the lab. We're going to see them now, but you can see it in both cross and longitudinal. Yeah, are Schwann cells only found in afferent? Can you find afferent? You can also find them in efferent. So yeah, Schwann cells can be here too. Good point. As long as it's in the peripheral nervous system, it can be found there. As long as it's peripheral, yes.
Oh, nothing that
Not in central.
In the myelin sheath, is there a lot of axons?
In a myelin sheath, are there a lot of axons? Within a single myelin sheath, it's covering one axon. So one axon myelin sheath, one axon myelin sheath, one axon myelin sheath. All encased in their own. And it doesn't extend, like it doesn't cover the whole thing. You can see that there are gaps. Those gaps will be important. We'll see why.
Is that technology what a nerve would look like?
I'm sorry?
Is that what a nerve would look like?
Is this what a nerve would look like? Yeah, this is a nerve. This is a cross-section of a nerve. A nerve, again, is a collection of axons. Good. A nerve is a collection of axons, so this is a nerve. Collection of axons all bundled together. Where were we talking about bundles of things before?
Fascicles.
There are nerve fascicles too. So, yeah. And they're covered by, yeah. Remember, or that nerve would be like epidurium, perineurium, yeah, same pattern. It'll be easy now. They know that you know much. It'll be easy for the nervous system.
Wait, so would that mean that within that myelin sheath, would it be
We're going to see why this myelin's important. I don't want to explain it yet. You'll see why it's important.
Thank you.
Another cell type that I just want you to know generally about, it's called the satellite cell. Satellite implies that it's just kind of somewhere nearby. So let's say we've got a satellite cell here. I don't know how to draw one. The satellite cell, very generally, just know that it supports neurons. It's found in the peripheral nervous system. They're a bit harder to identify. Basically, if you just see tiny cells surrounding these larger neurons, it's probably a satellite cell. When we get to lab and we look at peripheral nervous system neurons and glial cells, they'll be easily recognized. These are types of glial cells. Schwann cells are a type of glial cell. Satellite cells are a type of glial cell. They're types of glial cells, yes.
Sorry, what did you say about the satellite cells? They have tiny dots around.
Oh, satellite cells, neurons are fairly large. Their cell bodies are fairly large. Glial cells, their cell bodies are pretty small. So if you see a bunch of tiny cells surrounding a big cell, the tiny cells are
Oh, okay.
satellite. In the central nervous system, there is completely different glial cells. In the central nervous system, I'm going to start here on the right. In the central nervous system, we also want these myelin sheaths, but there are different glial cells that do it. Let's say here's the cell body of a glial cell, and it has these extensions that then wrap around the axon. This is called an oligodendrocyte. Oligodendrocyte. If you want to know why it's called that, if it helps you remember, we just talked about what dendro means. What does dendro mean? Branches. It has branches. Don't take Greek what oligo means. What's an oligarchy?
Isn't it like one?
That's a monarchy.
So then it's more than one.
It's a few. Yeah, more than one. Oligo means a few. A few branches of from a cell. With a Schwann cell, this is one cell, this is one cell, this is one cell. With an oligodendrocyte, you have one cell with several extensions that create several wrappings. That's why it's called an oligodendrocyte. They do the same thing. Oligodendrocytes and Schwann cells do the same exact thing. They create this myelin sheath that wraps around the axon. So same result, different ways. Oligodendrocyte you only find in the central nervous system. Again, we'll talk about why myelin is so important.
So oligodendrocytes are a separate cell that attaches.
Yeah, oligodendrocytes are a cell that send out extensions that wrap around sections of the axon. I'm working backwards here. So, whoops. Oligodendrocytes, things that wrap around. Microglia. We're probably not gonna have a chance to identify these in histology, but I do want you to know what they generally are. Microglia are a special immune cell that you find in the central nervous system. So this makes the second immune cell that we've discussed. What's the first one? Lysosomes are an organelle. Langerhans cells. Remember Langerhans cells in the skin? The stratum spinosum. Yeah, so this is yet another glial cell that does something similar. It's phagocytic. It'll eat things up and then use lysosomes to digest it. So we need a specialized immune cell. We're going to see why we need a specialized immune cell coming up, because we don't want our blood to directly mix with our central nervous. We learned about satellite cells. I'll just draw like a random cell here. We learned about satellite cells in the peripheral nervous system. In the central nervous system, a similar cell is the astrocyte. Astro, like stars, it's star-shaped. It's really branched in all different directions. Astrocytes are your jack of all trades glial cell. They do everything that, nearly everything the cell needs to does nearly everything to support neurons. I'm not going to get into all the details of what it does, but one of the major things that it does is that it forms something called the blood-brain barrier. Basically, there are blood vessels that go to our spinal cord and brain. We need blood. We just said that we have high metabolism in our neurons. But we don't want direct contact between the blood and the brain. Anyone think of one good reason why we wouldn't want direct contact? What the risk is?
If something gets into your blood.
Clots could be one, but more it's about protection from pathogens. We don't want to be immediately exposed to something. If we get an infection in our arm, not good, but not the end of the world. If we get an infection in our brain, that's really, really bad. So we want a blood-brain barrier. Basically, these projections we're going to see them wrap around blood vessels and create. Any guess what kind of junction? If we want to prevent leakage of stuff from blood into the nervous system, tight junctions. We're going to see tight junctions formed by these astrocytes. Well, we're going to look into this later. Yes?
You said that the projections wrap around the
Blood vessels.
blood vessels?
So let's say here's a blood vessel. I shouldn't draw astrocyte in the peripheral. Oops. Let's say here's an astrocyte. And one of its projections will like form this barrier and wrap around the blood vessel so it doesn't leak out. And there will be another one here that will get the next segment. And another one here that will get the next segment. So we're completely wrapping around all the blood vessels so that we're protecting. These astrocytes are gatekeepers. They're regulating what can go in and out of the central nervous system. We want nutrients to come in, we want to keep out pathogens.
What would be knowledge, right?
Brain and spinal cord, central nervous system. Amanda, then, is there another hand? Henry hands.
Are there gaps like in the Schwann cells?
Are there gaps in the, there are gaps between Schwann cells. So here's one Schwann cell, here's another, and there's a gap. And that gap will be important. There are tight junctions linking those projections of astrocytes, so there's no leakage.
So if a person has leakage, is that like a brain aneurysm?
If a person has a leakage, what would you call that? An aneurysm is if you have like a broken blood vessel, damage to a blood vessel. I don't know what you'd call it, but it's not good. That means that you're exposing your brain to whatever's in your blood, and that can be dangerous. I'm sure there's a name for it. I don't have one for you right now. Could be an aneurysm, I'm not sure.
So for an astrocyte, like, because it has multiple branches, would that wrap around the blood vessel?
Yeah, because this astrocyte has multiple branches, could it wrap around multiple blood vessels, or even the same one multiple times? It can, yes.
Not picture, are those artificially colored
Uh,
on the top branch?
Are these artificially colored? I mean, they're stained with something that makes them red.
Oh,
I think it's a staining. Pretty sure it's a staining. Yeah. The nuclei just stain.
So what are the other cells that are not?
Probably neurons. But honestly, they're not in very good resolution. I'll show you a lot better pictures later.
Are all the glial cells either one of these four in the central nervous system? Like if we see glial cells on histology, it's one of these four.
Yeah, if you see glial cells in histology, are they going to be one of these four? If we're looking at the central nervous system, it's going to be one of these four. If we're looking at peripheral, it's going to be one of these two.
Okay.
And this is going to be the simplest in that it's a Schwann cell if it's wrapped around an axon. So the hard part then is, can you identify an axon? And then if it's not, then it's a satellite. Here, if it's wrapped around an axon, oligodendrocyte, honestly, I'm not going to have you identify the histology microglia, so don't worry about that. We'll be able to identify this one, which I'll talk about in a second, because these are very distinct. They're always lining a space.
So will we have to tell apart in histology from astrocytes to the oligodendrocytes?
Will you have to tell apart astrocytes versus oligodendrocytes? Potentially, yes. Oligodendrocytes are only surrounding axons. Astrocytes are going to be like kind of on their own. They're off on their own.
So how do you like tell them apart? So like they're so those are more then?
How do you tell them apart? It's going to be a lot like this. I mean, I know this is peripheral, but you can see that the axon is surrounded by myelin. We can assume that since it's surrounded by myelin, we know in the peripheral nervous system that that's Schwann. If it were central, it would be oligodendrocyte. So the fourth one, ependymal cells, ependymal, ependymal. What these do, let me draw this, in our central nervous system, so in both the brain and spinal cord, there are spaces, there are fluid-filled spaces. And these fluid-filled spaces, it's filled with what's called cerebrospinal fluid. You may have heard of the CSF. It's the stuff you get out if you have like a spinal tap or something. CSF is the interstitial fluid of the central nervous system. We don't want blood to directly bathe our cells, so we want a filtered fluid. This is basically like highly filtered blood, so to speak. We want a highly filtered fluid surrounding our cells, cerebrospinal fluid. To form it, to form that cerebrospinal fluid, let's say here's a space of where cerebrospinal fluid is found. So this is a fluid-filled space down here. A special glial cell lines that space. Those are ependymal cells. So if you ever see a ton of cells lining a space, you know they're ependymal cells. Ependymal cells. So look at the nervous system and they're ever lining a space, whether it's brain or spinal cord. Ependymal cells.
So how could you tell the difference? Like, to me, when I looked at that, I thought that looked like simple column.
Yeah. How can you tell whether it's simple columnar or something else? It does look like simple columnar, I'll be honest, it does. Context. This is really zoomed in. If we have the whole picture, it'll be easier to tell. And again, it'll be really people at when I show the slides. But yeah, it does look like that. When you start to see neurons surrounding it, then you're like, okay, it must be nervous system, and it's saying it's lining space. Okay, a lot of different cells, right? We've got different types of neurons. In the peripheral nervous system, we've got satellite Schwann cells. In the central nervous system, we've got oligodendrocytes, microglia, astrocytes, and ependymal cells. Okay. Glial cells and neurons all make up nervous tissue. They all have their roles. So you can see. Oh, here's one way you can tell. Brooke, were you asking? Oligodendrocytes. Just to give you an idea of how exactly are these Schwann cells and oligodendrocytes creating this myelin. Here's a cross section of an axon. Here's a Schwann cell, and it's the same for an oligodendrocyte too. So same basic process. Schwann cell or oligodendrocyte just starts wrapping its membrane around a ton of times. That heavy wrapping of membrane, that's what myelin is. So if you see a neuron and you see cell bodies right next to it, immediately adjacent to it, and we're talking about the central nervous system, then we can say that that's an oligodendrocyte. If we know we're in the peripheral nervous system, this is longitudinal. You can see nuclei here, and then this lighter space, that's the myelin of a Schwann cell. What is the major molecule then that forms myelin? Is it protein? It's not protein. Lipids, phospholipids. Phospholipids are the major component of myelin because it's literally just membrane wrapped tons of times around axons. Sorry.
Wait, you said the major component was
Specifically phospholipids, but lipids.
okay.
Does lipid mix well in water? No. What do you think conducts electricity better? Lipids or water? It's like you don't want to put toaster in the bathroom. And we know that neurons conduct electricity. So does anyone have the term for what these lipids are acting as? Oops. If something that allows electricity to flow is called a conductor. Insulator. This is acting as an insulator. It's an insulation. When you have insulation in terms of warmth, you wrap yourself with a blanket to keep the warmth in. If you're a neuron and you have lipid wrapped around yourself a bunch of times, you're keeping the electricity in. It's like if you have an electrical wire, we cover the wires with this rubbery stuff, right? I don't actually know if it's rubber, it's a rubber compound, but it doesn't conduct electricity is the point. This wire is insulated. Because if it weren't insulated, it would be really hard for the electrical signal to get from point A to point B. We lose that signal. Similarly, this myelin helps keep in the electrical signal for neurons, helping the electrical signal more easily pass from point A to point B. time. Answers on 3. 1, 2, 3. On 3, it's a letter. 1, 2, 3. D. D. It's D. Ependymal cells, they line those fluid-filled spaces. They also help reduce the fluid. Ependymal cells. Raise your hand if you need more time. That's on 3. 1, 2, 3. On 3, say letter. 1, 2, 3. Astrocytes, those are the ones that form the blood-brain barriers. That's what damage to one other things. Cool. Okay. You know the basics now of nervous tissue. Now, how do they function? So what I'm showing here, what this diagram is showing right here, let's say we're looking right here. Here's an axon terminal of one neuron. Here's the dendrite of another. Axon terminal of one neuron, dendrites and cell body of another neuron. So one neuron communicating with another. We're looking at a synapse. We're looking at a neuronal synapse. The way neurons are activated is a lot like that strong person game that I mentioned at a carnival. I don't know, you can't see it very well, but like this guy's got a hammer, you use a hammer, you hit the target, and you can hit the target as many times as you want or whatever, but you can hit it as hard as you can, but you only win a prize if you hit it hard enough that you get the light or whatever the thing to make it all the way to the top. In other words, to win a prize, it's all or none. If you hit it just hard enough or really, really hard, it doesn't matter. You still win a prize, as long as you hit it just hard enough. There's a threshold. Neurons work in the same way. You have to reach a threshold of activation. What is the threshold? We're not talking about hitting anything. The stimulus, here we have neurons, what do they release? Sorry, what does this neuron in the axon terminal release into the synaptic cleft? Neurotransmitter. You're getting ahead of yourself. I got a space here. All right, let's say here's the axon terminal. Here's the dendrite cell body of another neuron. In the axon terminal, you've got neurotransmitter that can be released by exocytosis. Here's neurotransmitter being released by exocytosis into the synaptic cleft. Neurotransmitter is now going to bind onto a. That's for a muscle fiber. Receptor. We have a receptor here that the neurotransmitter can bind to. All right, neurotransmitter released from the axon terminal. Color here. Receptor gets activated. We've seen this happen before. A receptor gets activated. What happened with muscle fibers? Before that. Go back to what you thought before. What's the next thing that happens? Not calcium, sodium. The channel opens up. The gate opens up. We've gone from a receptor protein, and receptor protein is also a transport protein. Yes. The channel opens up that lets sodium rush in. Same process we've seen for muscle fibers. It's a different receptor, but same basic process. Neurotransmitter binds, receptor's activated, channel opens up, sodium rushes in. We get that rush of sodium. Sodium has a positive charge. And the movement of charge, that's what electricity is. Right where you opened up that channel, that membrane protein, the transport protein, that's where it's going to be most positive, because it's all clustered there. And the more that sodium comes in and then spreads out by diffusion, the more it spreads out. Because it's more spread out, which area is more positive? By the channel or out here? It's going to be more positive by the channel because that's where it's concentrated. The more it spreads out, the less positive it is. It's just not as much. There's a gradient. There's a gradient of charge. Very positive, kind of positive, not so positive. So the term for this, the term for what's happening here, that's called a graded potential. Because there's a gradient of charge as sodium flows in. So that's the first question is, did we hit it hard enough to activate our neuron fully? Okay. This presynaptic neuron sent to neurotransmitter, bound to the receptor, lets sodium in. Now what happens? Back to our drawing here. There's this one region of this neuron that has a special name. I mentioned how the dendritic end, that's the integration, the input. The cell body is the integration. The axon's the output. The cell body is the integration, it's the decision point, because this is where we decide if we hit the bell or not, if we hit it hard enough. There's this part right between the cell body and the axon. It's called the axon hillock. Hillock. Axon hillock. This is our decision point. This is our bell. We can only hit our bell if we got enough strong, it's called depolarization. If we got enough sodium to get into the cell, if we got enough sodium to make its way to the axon hillock, then we've activated our neuron. Here's the axon terminal, dendrites and cell body. Here's the axon hillock and axon. If enough sodium, if our graded potential is strong enough, if enough sodium has made its way to the axon hillock, then we get what's called an action potential. So in the dendrites and cell body, that's where a graded potential happens. In the axon, that's where we have something called an action potential happening. It's also electricity. That's why the word potential is referring to the electricity. It's also electricity, but it's a sure thing that it'll happen. Graded potential, we saw, goes down over time and space. Action potential will make it to the very end of the neuron. So the action potential is going to sweep from the axon hillock all the way down to the axon terminal. The action potential will sweep from the axon hillock all the way down to the axon terminal. Only if enough sodium is made it to the axon hillock. That's why it's a decision point. Yes?
And is this movement of sodium just due to time, or can it fail? Like, is it just that you need a certain amount of time that it's just going to reach it? Or?
You mean to the axon hillock?
Yeah.
That's a good question. The question is,
I don't know, is it just that it's a matter of like time of, you need a certain amount of time for the sodium to get to the hillock, or is it?
So this is a really good question. He's asking how, like, to activate this axon hillock, is it just the amount of time? Like, is there a certain time range you can activate it, or like the amount of strength? Both. You're going to learn in physiology a little bit about temporal summation and spatial summation. So really quickly, yes, if you get like, this isn't the only axon terminal that's likely setting input. So there could be a bunch of axon terminals that activate at the same time. You activate at the same time, then you get all this input, and then you can activate it. If this is a small signal, a bunch of small signals added together could lead to one really large signal. Or let's say it's just this one neuron small signal, but it releases a bunch of times in a short amount of time. That can also activate. That's temporal and spatial summation, and you'll learn about that. Yes.
So is there anything else in the space of the cell body that like?
Is there anything else in the space of the cell body? You learn this in physiology too. It's a regular cell. It has all these organelles here that also get in the way of the ions flowing through. It's called resistance. So that does get in the way. Yes. You have a nucleus. You've got a bunch of organelles all over there.
Can you repeat what an action potential is?
What is an action potential? I'm going to explain it here, and then let me go give this other question. Because I've only mentioned what it is here.
Okay,
Yeah.
that's
So if your gradient potential is strong enough, you'll activate something here in the axon hillock that leads to what we call an action potential. So what is an action potential? Over here, at the dendritic end, we had a receptor that was activated. How is a receptor activated? How would you describe this type of activation? Secretion of something? A chemical? This is a chemically gated channel. It's chemically gated. You need a molecule, a chemical, to bind to a receptor to open up the channel. Chemically gated. So that's a chemically gated channel. At the axon hillock, we have a special kind of receptor channel. It's not chemically gated. It's voltage gated. The axon hillock, we have voltage gated channels. So when that graded potential reaches the axon hillock, now the voltage gated channels get activated. Again, only if it's strong enough. They have a certain threshold of when they get activated. If it's strong enough, then it'll open up. Voltage gated channels open up. Voltage gated channels open up. Sodium rushes in. There are more voltage gated channels over here. Channels open up, sodium rushes in. There are more voltage gated channels over here. Channels open up, sodium rushes in. It goes on and on and on until we get to the end. That's what I mean by this all or none response. If it happens, it's going to happen. It's inevitable, barring anything wrong with the neuron. Right.
I was gonna ask, where is the chemically gated channel?
Chemically gated channels, you find those in the dendrites in the cell body. It's mostly dendrites, but you can also find the cell body. So when an action potential gives you a domino effect. You activate the axon hillock, it will go all the way down the axon reliably, barring any disease, such as disease. Yeah.
Are neurotransmitters originating from the cell body, or is it made in the cell?
Where are neurotransmitters made? They're actually made in the cell body and then transported by vesicles all the way down. Yeah. Charlotte,
So if you reach action potential in one neuron, does that mean that the activation of each individual neuron act like if it was a string?
if you activate the action potential in one neuron, what does it happen to the next neuron? In most cases, action potential in one neuron leads to neurotransmitter release, which could potentially lead to activation of the next neuron, which is dependent.
But if you don't reach action potential, it kind of like stops the.
Like even if you release neurotransmitter here, you're not necessarily going to cause an action potential in the next neuron. Great questions. Thanks everyone. I'll see half you axon over here. Let's see axon here. Good. 3, I guess I could have been more specific here. Now I would ask you. I could ask a few things here. If I ask you for what this overall structure is,
It's the axon.
it is part of the axon, but it's what's wrapped around the axon. It's a myelin sheath. let's say this is in the peripheral nervous system, and we can also assume that because this is an individual cell with wrapping. So these are individual cells wrapping around each part. What kind of glial cell is this? This is a Schwann cell. This is a Schwann cell. You can see the nucleus and you can see its membrane wrapping. Like the actual axon is this middle part,
Yes.
and then the myelin sheath made of Schwann cells is what's wrapping around.
But you are asking here about Schwann.
Well, I wasn't very specific, but it depends how I ask it. If I'm asking what is the material, it's a myelin sheath. If I'm asking the cell, it's a Schwann cell.
So in a model, the Schwann myelin sheath look different from the like,
Yeah, how would it look different for an oligodendrocyte? Here you can see the nucleus with all of its membrane wrapped around it. If it were an oligodendrocyte, the nucleus would be off to the side with one extension wrapping around, with another extension wrapping around. The nucleus would be farther away. So we can assume that this is a peripheral neuron. A neuron in the peripheral nervous system, axon in this case. All right, let's go over the next thing. So these models will appear on the practical, so expect this. All right, question 4. This is a superficial dissection. This is a deeper dissection. So this is pectoralis major. This is pectoralis minor. You see pectoralis minor. What are these muscles down here? Serratus anterior. So 4 was pectoralis minor. 5. Again, this half is the deeper dissection. You can see the abdominal aponeurosis, see rectus abdominis, and the external obliques because they're going down and in. What I'm pointing out are the muscles that are going up and in. These are internal obliques. They go up and in. 6. We're looking at the anterior portion of the arm. This is the biceps brachii, but it's underneath the biceps brachii. Brachialis. This is brachialis. Good. This one. Here we're looking at the back of this person. Again, superficial, so this is trapezius, so we're looking deeper. It's going from the top corner of the scapula up to the neck. Levator scapula. This is the levator scapula. We don't see it on the cadaver because the neck's off, but it's clear here. Levator scapula. Basically, if I'm going to ask you about levator scapula, it has to be on this. Here, also a deeper dissection. We've removed the trapezius. I'm pointing to this top one, not to this. Yeah, it's connecting from the spine to the scapula. Rhomboid minor. Here's rhomboid minor. This would be a rhomboid major. This bigger one down here. Rhomboid minor, rhomboid major. Right. Number 9, also a deeper dissection. Here we have the gluteus maximus. This would be medius. If it's connecting to the very top of the crest, it's medius. Connecting to the very top of the crest is medius.
Can you show us on this one the last one?
Minimus? Gluteus minimus. I don't know if this minimus or piriformis, but it would have to be deeper in, like down here. This is a part of it. It would have to be this one right here. Question 10. We're looking at the leg. Okay, we're looking at the lateral portion of the leg. Here's anterior. Here's the tibia. just next to the tibia, that's tibialis anterior. So this is tibialis anterior. The next muscle over, you can see it's going down and connecting with the toes. This is extensor digitorum longus. This is extensor digitorum longus. So tibialis anterior, extensor digitorum longus. Next one, very lateral, going down to the ankle, fibularis longus. Fibularis longus. 11 is a deep dissection. Here you can see the gastrocnemius connecting with the calcaneal tendon. If you cut away the gastrocnemius, you can better see the soleus. 11 is the soleus. The soleus is underneath, it's deep to the gastrocnemius, it's deep to the calcaneal tendon. So it goes all the way down here. It goes all the way to the bottom of your ankle. Soleus. So what? There's only two major muscles back here. There's a third one, but it's smaller. Two major muscles back here. Gastrocnemius is the big one superficially. Soleus is the one underneath. So you can see it. This is gastrocnemius cut away, and so here's a gastrocnemius continuing down. This next layer is the soleus. Number 12. Again, another deep dissection. We're talking about the hamstrings. Here is the most lateral one. That's biceps femoris. Most lateral is biceps femoris. And then we have these two muscles. One on top and longer, and one underneath, which you can better see where I put the sticker. So this long one that's cut off here, that's semitendinosus. The one that's deeper, semimembranosus. Tendinosus, semimembranosus. Cool? Wonder who got all right. So there's a lot to review, I know. We're going to have time in the class, half class review everything. Question?
Do you see the psoas?
You see the psoas? No. You see the? You can barely see the psoas here. It's just the last portion of it. So here's a deeper dissection, and you can see this muscle kind of creeping in right here. It's coming up from deeper in the pelvis. This would be the psoas. If I show you the psoas, it's probably going to be on that rack of ribs model, because you can more clearly see the whole thing. But yeah, you can see just a bit of it, and you can't see the iliacus. Cool. Practice will be just like that, like always. All right, hey everybody. So we're going to continue talking about. We're going to continue talking about the nervous system. You do have a lab check, and I'm hoping we can finish it by. We left off talking about neurons in general. All neurons function in the same basic way. All neurons function in the same basic way. They have graded potentials that can lead to action potentials. All right, here's my generic looking neuron. Here's a nucleus. These are dendrites, axon hillock, axon terminals. Could have more than one branch. What happens with graded potentials is that we have receptors here. These are chemically gated. Chemically gated receptors and channels. So a neurotransmitter or some chemical binds here. Neurotransmitter binds here on that receptor. It opens up a channel. sodium rushes in. That's our graded potential. What differs about the axon hillock and the rest of the axon is that we don't have these chemically gated channels. We have voltage gated channels. So, I should drop that. So at the axon hillock, we have, starting at the axon hillock all the way down the axon, we have voltage gated channels. If this graded potential is strong enough, the voltage gated channels here at the axon hillock get activated. So sodium is flowing through, we get enough sodium to reach here, we activate this channel. Channel opens up, sodium rushes in, which will then activate the next set of channels. Which will then activate the next set of channels, and so on, and so on, and so on, until we get to the end. So this is the graded potential. Here is our action potential. If you activate this, the rest will be activated barring any conditions, which we'll talk about an example where it's done. Graded potential, you may or may not activate the action potential. Right, so that's the gist of an action potential. Any questions on that? I said that neurons are important because you're sending an electrical signal from dendritic end to axonal end. It's within the neuron. Most neurons, the electricity just flows within the neuron. When we get to when the action potential reaches the end, that is the trigger for neurotransmitter release. The action potential, when it reaches the axon terminal, that is the trigger for neurotransmitter release. So where did this neurotransmitter come from? It came from a neuron. That means that neuron had an action potential that reached the end here, and then that caused the release of neurotransmitter. We're not going to go to the mechanism of how that leads to the release, but know that it does. Here at the axon terminal, we've got a bunch of vesicles waiting to be released. They need the signal, and the signal is the action potential. How did these vesicles full of neurotransmitter get here? We've got all the ribosomes, rough endoplasmic reticula, and Golgi here, and then you send the vesicles along a special microtubule network to the end, just waiting to be released. So it's just this constant pattern of activate, graded potential, action potential, neurotransmitter. Activate, graded potential, action potential, neurotransmitter. Over and over and over again until you reach your final target. Let's say the muscle you lead to contraction. Questions on the basics of how a neuron works and what these structures are important for? Oh, what does it imply about what neurotransmitters are made of? What type of molecule? Stored vesicles, proteins. Neurotransmitters are mostly proteins. There's always some exceptions. Neurotransmitters are mostly protein-based. Yeah. Back to the myelin sheath. Oh, sorry. Go ahead.
Sorry, so the neurotransmitters can give a graded potential and then the action potential and they go through again to the next.
Yeah, I'll repeat that. Neurotransmitters cause the graded potential. Graded potential, if strong enough, leads to the action potential. Action potential leads to neurotransmitter release.
And the reason why it wouldn't be strong enough is because of the other organelles in the cell body?
Why wouldn't this be strong enough? Could be because there's organelles in the way. Could be not enough sodium entered. because this isn't the, like, I've only drawn one here, there's tons all over. So you can activate one, you can activate all of them. Depending on how many you activate, that can lead to more or less graded potential, more or less signal. It's like if people were trying to rush in to get to a concert, you can open one door, you can open 10 doors. You can let people in slowly, so you're not going to get much signal. You can let people rush in all at once. So here, you could open one, or you can open a ton. If you open, the more you open up, the more likely it is you're going to activate.
So the neurotransmitter causes the chemical gates to open, which causes the sodium to flow, and then if it's strong enough or enough sodium is released or flowing, then it's that action potential, the voltage gate opens, and then action potential goes all the way down the neuron, the axon, and then does it stimulate the release of neurotransmitters like at the other end?
Yeah.
So it's kind of like a domino effect.
Yeah,
on
when
top
the
of
action
domino
potential
effect.
reaches the end, then the electricity that reaches here to the axon terminal, that causes neurotransmitter release.
Okay. So is that like a domino effect, enough domino effect kind of thing? Right, because the neurotransmitter's on one end, but it's also.
Yeah, the start of the domino effect, where does it start? It starts right here. The axon hillock is our decision point. This is where the first domino is pushed. If you, let's say you've got a bunch of dominoes lined up, you can tap the domino, but if you don't hit it hard enough, it won't fall. Here we hit it hard enough, we get enough voltage.
So the neurotransmitter's hitting the domino.
Neurotransmitter is trying to hit the domino, yes.
And then,
Or really it's the sodium, I guess, the
Okay.
amount of sodium you have here.
okay,
Great.
but then it causes neurotransmitters to be released at the other end.
Yes.
Okay. Okay.
Okay, another fun thing to think about, which I'm only going to mention as this one fact. Membranes are leaky. So we know that membranes, we have special transport proteins that can let things in, but there are also transport proteins that can let things out. So just think about, like these are ones that we want to let sodium in, but there's also channels, other random channels here that just let charge leave. So charge is leaking out. It's like a leaky hose. Like let's say you've got a hose, you've got a bunch of holes in it. You want water to get from point A to point B, but along the way you're losing some water because it's leaking. Same thing here. You're leaking charge because membranes are just leaky. You'll learn more about that in the leak channels. What that means is, if you're leaking charge, it's going to be slower for your sodium to activate the next channel, It'll be slower for the action potential. So there are neurons that are just leaky, and they just happen to be slower. You ever have a dull pain? Like, you know, there's sharp pain, but then there's also dull pain. Dull pain, that travels by weaker axons. That's why it's slower. But if you want to control things like our muscles, we want quick, rapid response. If you want to process things in our brain, we want quick, rapid response. We want to make sure the action potential is very quick. One way that we can increase the speed of our signal is by insulating this. So if you have all these leak channels here, we want to cover them up. What better way to cover them up than with more membrane? That's what myelin does. Myelin covers up where leak channels would be. You're preventing leakage of current. Sorry? It's not leaking to the same extent now. Because you're covering it up. So it's not going to leak. The myelin is covering the leak channels. Yes? Does it cover all leak channels? No, but a lot of them, a significant amount. With dull pain, with the neurons for dull pain, there's no myelin. There's no myelin, so it's just slower. You'll notice that I drew it as segments. It's not covering everything like a normal wire would. You see like electrical wires. At these segments, we need to keep the charge going. You can see that we need voltage gated channels at different segments to keep recharging the action potential. Those are called nodes of Ranvier. On French here. Nodes of Ranvier. These are spaces where you find more voltage gated channels. You have voltage-gated channels starting here at the axon hillock, and you have more voltage-gated channels found at the nodes of Ranvier. So these gaps are critical for how a neuron functions. You don't want myelin to cover everything. You want to insulate pieces, and then in the gaps you recharge the action potential. So sodium flows in because of the voltage-gated channels. Sodium just has to travel a little bit. It won't leak out because you've got insulation. Activate the next set of channels. More sodium rushes in. Won't leak out. Activate the next set of channels, and so on. Myelinated neurons have very quick transmission. One example is all of our skeletal muscle, all the somatic motor neurons, they're myelinated. They should be myelinated. What would happen if you lost your myelination when you normally have it? You might not have control. You might not be able to send an action potential. There are conditions where you lose that myelination, like ALS, Lou Gehrig's disease, or multiple sclerosis. Those are dangerous. I mean, it sucks to be paralyzed and you can have loss of control, but remember our muscles of breathing, diaphragm, that's a skeletal muscle. If you can't control that, then you can't breathe. Yeah.
What did you say about myelinated neurons? They are
They have faster signals. Myelinated neurons, if you have axons that are myelinated, you'll have a faster signal, faster action potential. If you demyelinate axons that are normally myelinated, you'll have slowed, possibly stopped action potentials, lead to lack of control, other neurological problems. Because that charge is leaking out when it normally shouldn't be.
demyelination is what causes these like Lou Gehrig's.
Yeah, and MS.
I kind of got a stupid question.
What's up?
At the node of, how do you say it again?
Node of Ranvier?
Ranvier. If sodium is leaking out, but where's the other sodium coming from?
So, if sodium's leaking out, where is it coming from? So it's actually not sodium leaking out, it's potassium. I don't want to get into that detail. Potassium is another positively charged ion. So sodium rushes in, but potassium can leave. And that's what actually, it's about the charge, not about so much about the what it is.
So that's kind of like a
So
membrane.
sodium's coming in because we created a gradient in the first place with the sodium potassium pump.
Okay.
There's more details that I just glossed over.
Okay.
And if you want to talk about it later, I'm happy to. But this is something you're going to cover in physiology.
Okay.
Someone was asking me about sodium potassium pump. It has a lot to do with that.
Sorry, I'm confused. How do you know those voltage-gated channels versus the node?
Within, the node is just the space,
Is the space?
the segment of the axon. The node is the segment of axon that's not myelinated. In the segment of axon that's not myelinated, you find voltage-gated channels. And you also find voltage-gated channels in the first segment, which is we just call the axon hillock. So from the axon hillock all the way down to the axon terminal, in the spaces, you have voltage-gated channels. Take a moment. Raise your hand a few more times. Hands on three. 1, 2, 3. Ah, funny. Talk to someone with a different answer. All right, go ahead. 1 minute. How's the difference? Alright, one more time, please. Hands on three. Back here. 1, 2, 3. Okay. On 3, say the letter. 1, 2, 3. Yeah, we're in the central nervous system. Spinal cord tells us we're in the central nervous system, so it has to be oligodendrocytes, not Schwann cells. Spinal cord tells us we're in the central nervous. Oh, oligodendrocytes. Another question. Another question. Raise your hand a few more times. Hands on 3. 1, 2, 3. On 3, say the letter. 1, 2, 3. Bees. B. Plasma membrane made of phospholipids. That's what's acting as the insulation. It's the membrane of those cells, oligodendrocytes and Schwann cells, it's wrapping around the axon. So this is what I drew here in green. It's just a bunch of membrane wrapping around the axon, insulating those axons. Okay, now here's the fun part, histology. Neurons come in all shapes and sizes. You always see them drawn like this. This is our generic looking neuron. Some neurons look like this. Not every neuron looks like this. Here's a bunch of different sketches, simple sketches of what some neurons look like. What they all have in common is that they have some end that has dendrites in the cell body and some end that has axons and axon terminals. It can vary how many dendrites they have. It can vary how many axons or axon terminals they have. Some are really simple. Like here's a really simple cell. Here's a cell body, a few dendrites, one major axon. Here's a really complex one. Here's a cell body. All of this, these are dendrites. So they vary. And we're going to get used to seeing some different types. They vary based on location and how they look. And I'm going to give you a guide of how you can identify the different ones. In general, if we're talking about a sensory neuron, a neuron on the afferent end, it's going to be one of two shapes. If we're talking about a sensory neuron, it's going to be one of two shapes. If you remember, if you took pictures of how I drew it in the class before, I drew it in a very specific way. I had the cell body over here. I had the axon like this. Dendrite, axon terminal. The cell body's off to the side. The term for this, I'm getting ahead of myself. I'll start. The term for this is pseudo unipolar. Pseudo-unipolar. That is one type of sensory neuron. Dendrites over here. cell body. This whole thing is the axon. Axon, terminal. That's the whole thing. The shape is called pseudo-unipolar. Pseudo means fake or false. Unipolar means one pole, one direction. Every neuron has to have two directions because you have a dendritic end and an axonal end. It just looks like it's all axon. That's why it's pseudo-unipolar, because this whole thing is the axon. So normally the dendrites are with the cell body, but the dendrites are here off on their own, connected directly to the axon. That's one major type of sensory neuron. And the sensory neuron, this axon will be the afferent. That would be the afferent. Another thing, the dendrites and cell body, the dendrites and cell body, they're found in the peripheral nervous system. So if it's myelinated, what kind of cell would you have? Schwann cells. The axon terminal, though, the axon terminal is in the central nervous system. The axon terminal, it has to communicate to the central nervous system, to the brain and or spinal cord. So the axon terminal is found there. Most of the cell is peripheral. This segment of the cell is central. That's one type of neuron, pseudo-unipolar. Here's another type. This is probably the most basic type of neuron you can find. It's a bipolar. This is pseudo-unipolar. This is bipolar because you've got one side that's dendritic. You got your cell body in the middle, and you got your axon terminal at the other end. Also in the central nervous system. Two major cell shape types you find in the sensory end.
They both look the same.
Sorry?
They both look the same.
They both look the same. Here the dendrite goes straight to the cell body, which then goes to the axon terminal. Here the dendrite goes straight to the axon and axon terminal. Cell body's off to the side.
So that neck is what makes it.
Cell body's off to the side.
Okay.
That's what makes it
It's
pseudo-unipolar.
like you can remember from uni, like one,
It's higher up, and it forms a one. Actually, yeah.
Says he's blockaded, obviously peripheral nervous system, central and peripheral again. What is this signify?
Why do I write it 3 times? This is the sensory. This is brain or spinal cord. This is the efferent end.
Okay.
This is afferent. This is afferent with E. Okay. In the central nervous system, we call them interneurons. So these are sensory neurons. Let me show you an interneuron. Interneuron, it's in between. The shape of all interneurons is multipolar. What that means, you've got your cell body, you've got lots of dendrites. Lots of dendrites coming off the cell body. And then usually one major axon. The axon terminal. It might branch, but I'm not going to draw it branch. Lots of dendrites to the cell body, axon, axon terminal. Again, this is called multipolar. Those are interneurons. They're multipolar. They're multi because they have lots of dendrites and sometimes lots of branches. Sometimes they have branches of axons.
What is that branches?
These are axonal branches, these are dendritic branches. So this is lots of branches of everything.
So the dendrites for that one come straight off the body? It doesn't have an
Yeah,
axon?
dendrites here come straight off the cell body.
Okay.
Doesn't really have much of a neck.
And these are interneurons,
Interneurons found in the brain and spinal cord.
and they're multipolar shaped.
All the shape is multipolar. You'll notice that they are found exclusively in the brain and spinal cord. Here for the sensory neurons, the axon terminals are found in the spinal cord. Both dendrites and axon terminals are found all within the spinal cord or brain. Found only in the brain and spinal cord, all of it.
So are those neurons doing most of the receiving to send off to the sensory
These
neurons?
these interneurons, they're the ones that are receiving information from the sensory neurons.
From the okay.
And they're also, so here, let me just draw a connection here. Let's say, okay, let's say we have a neuron here. It's communicating. Yeah, so a sensory neuron communicates with this interneuron. Now our interneuron, not only can receive information, it can also send out information. So switch to a motor neuron, its dendrites and cell body are also in the central nervous system. For a motor neuron, its or efferent neuron, I should say, efferent neuron, its cell body and dendrites are also in the central nervous system. You find it in the brain and or spinal cord. It is also multipolar. And then this can lead to other places. Effector or motor neurons, because we have an output of signal. We're controlling something. Could be muscle, could be glands. So that's why effector might be the more appropriate name, because motor implies you're controlling muscles. Dendrite cell body in the central nervous system, but axon and axon terminals are found in the peripheral. So if this is myelinated, what kind of, Schwann cells, thank you. You find Schwann cells are wrapping around here, Schwann cells could be wrapping around here. The difference is axon terminals for sensory neurons in the central nervous system. Cell body and dendrite of motor neurons and efferent neurons are found in the central nervous system.
It's probably a student question, but is this for every single peripheral nervous neuron? Is all of their axon terminals are in the central nervous system?
Are all axon terminals of peripheral sensory neurons in, I'm going to say majority, that's obviously a good question. Candace, your question too is a good one. I'm going to say majority, I'm not going to say all. There's probably an exception that I'm not thinking of.
Okay, so in regards to like the test.
In regards to our test, sensory neurons on the whole, the axon terminals, and the central nervous system. We're going to learn, we'll get to the nitty gritty later, but this is our overall trend, what we see. So, like I was saying, you've got those shapes. What kind of neurons are bipolar? they're in very specific places. You find bipolar cells, bipolar neurons, in your olfactory epithelium, so lining your nasal cavity. For vision, so in the back of your eye. On your tongue, for taste. For hearing, so in your inner ear. And then something called your vestibular sense, it's your sense of balance. So it's only for very specialized senses, the ones that you traditionally think as your 5 senses. Except touch, not touch. Touch and pain and itch, that's pseudounipolar. So Meissner's corpuscles, Basidian corpuscles, those are the ends of pseudounipolar neurons. So this could be like a Meissner's corpuscle, or something like that. This could be a Meissner's corpuscle that then leads to the central nervous system. Touch, temperature, pain, anything that you detect on your skin, anything that you detect on your skin, that's what somatosensation is. We're gonna. Yeah, Meissner's corpuscles, Basidian corpuscles, the neurons that communicate with Merkel cells. Those Merkel cells communicate to neurons. Merkel cells, remember, are a special. Merkel cells are special because they're special sensory cells. So let's say here's a Merkel cell. The Merkel cell is neuroepithelium, it's not a neuron. But the Merkel cell can send a neurotransmitter to a neuron that then communicates with the spinal cord innervation. Muscle spindles or nerve endings like Meissner's corpuscles. The only special receptor cell that we've gone over is Merkel. We're going to go over a few more. And for vision, for hearing, they're special cells. Taste as well. So sensory, pseudounipolar and bipolar. Pseudounipolar is for somatosensation, things you feel on your skin like touch, temperature, itch, pain. Multipolar you only find in your central nervous system and efferent neurons, motor and other neurons. Here's a pseudounipolar neuron. See the cell bodies off to the side. This whole thing is the axon. Here's bipolar cell bodies in between dendrites and axon. Here's multipolar, lots of dendrites, often non-terminals, but usually one major axon. Pseudounipolar. Pseudounipolar has the cell body off to the side, dendrites initially connected here to the axon. This whole thing is the axon. What's the benefit of having the cell body off to the side? That's a good question. Simple answer. When you have bipolar neurons, the neurons are typically short. So they're often not myelinated. Since they're so short, you don't need myelination to send the signal quickly. It's short. When you have a pseudounipolar neuron, you can cluster all the neurons together in a space, which we're going to mention in a second. And then you can also bundle the axons together into a nerve. And I guess you can just regulate where those pass through. Usually for pseudounipolar neurons, the axons are really long. They tend to be really long. And so you need a way to bundle up the axons together. Where do you find multipolar, central, and the motor neurons, which are extended to the peripheral? So motor neurons extended to the peripheral. Really, if you find a cell body in the central nervous system, it's going to be an interneuron. And why does why does a multipolar cell shape make sense for an interneuron? It's receiving a lot of information and sending out a lot of information. You need a lot lots of branches of dendrites, lots of branches of axons. Structure relates function. Take a moment. Exactly. One more time. Answers on 3. 1, 2, 3. Here's your letter. 1, 2, 3. Hey. It's bipolar. You can see a neuron cell body here. This is a better one. Neuron cell body. You've got dendrites in one end, axons leading to another end. This is called a bipolar cell. And for a special thing like sensing vision, sensing light. A few more times. Hands on 3. 1, 2, 3. Find some with a different answer. Talk about it. 1 minute. Go ahead. All right, one more time, please. Hands on 3. 1, 2, 3. 3, say the letter. 1, 2, 3. A. What we're saying is we're testing a reflex pathway. A reflex pathway is where you detect something, you send that information to our interneuron in the brain and or spinal cord, and then we send a signal outward to the muscle in the afferent pathway. I said that in the second sentence, you know the pathway of the spinal cord to the muscle is not damaged because you can directly stimulate the nerve, so you can stimulate the axons here, these afferent axons. You can stimulate them, and you can still cause contraction. So you're sending an electrical signal here, you can still cause muscles to contract. This one's fine. What must be damaged is over here, the afferent pathway. And sympathetic and parasympathetic, those are also afferent types of afferent pathways. So it's not that. Cool. That brings us to what a reflex is. We've basically drawn a reflex pathway here. And you've noticed, I want you to pay close attention to how I've been drawing these neurons. You will be drawing the reflex pathways coming up next week. Draw your dendrites like this. Draw your cell bodies like that. Draw your axon terminals like that. And you have your different shapes. Draw, yeah. You've been drawing this whole time. Every week. What is a reflex? A reflex is something where it means voluntary effort response, and it doesn't necessarily involve the brain. So what should it involve?
Spinal cord.
Should at least involve the spinal cord. Or the brain, or both. When you think of reflexes, you might think of like cat-like reflexes, like doing ninja type stuff. That is an example, like you automatically do things quickly, but it could be something more mundane, like just shining a light on your eye and your pupil constricts, or knee-jerk reflex where you tap your knee and kick it out. Those are also reflexes, they're automatic. Any automatic thing where you have a detection of something, integrate it, and then you do something, that's a reflex. It follows this path, it's a reflex. From peripheral to central to peripheral. So that's what a reflex arc is. We're forming this arc from sensory to the central nervous system to motor. Following a reflex arc. Activate a sensory receptor with some kind of stimulus. Could be light, could be sound, could be touch, whatever. Send it, relay it through an afferent pathway to the central nervous system. You decide what to do with that information. You send information out through an efferent neuron. And we have some effect. It could be controlling the muscle, controlling the gland, controlling something. Yes?
Another stupid question. Are dendrites thinner than the axon terminals?
Are dendrites thinner than axon terminals? Generally, it depends. Dendrites can change in size. They can even change over time. When we learn, for instance, here's a side note, we learn like dendrites tend to get bigger and wider. So when you strengthen a neural pathway, it gets bigger. So generally they're smaller, but they can change size.
So that's not a good way to determine.
Not a good way to do it.
Okay.
Reflexes, I'm going to skip over this, hold on, for the sake of time. Or that, for the sake of time. I just want to get to the histology. Okay, so note to self, or note to all of you, I may or may not get back to this. I'm skipping 28 to 28 to 32, I'm skipping for now. All right, this is the part I want to get to. So, your nerves are bundled together. A nerve is a bundle of axons. That's what a nerve is. So, like here you have one neuron. I've drawn one neuron here. It's not the only neuron leading to the central nervous system. You've got another one over here, and another one over here. And all the axons are bundled together. That bundle of axons is a nerve. And a nerve that goes into the spinal cord is a spinal nerve. And guess what? They're bundled together just like muscle fibers are. A single axon with its myelin sheath is covered by a protective connective tissue known as endoneurium. Endoneurium. Endoneurium is what directly covers one axon with its myelin sheath. So here you can see a bunch of axons covered by endoneurium. Okay, it's following the same pattern. Just like endomysium with this endoneurium. All these axons are bundled together and then covered by another connective tissue layer called perineurium. So here's a fascicle, and the fascicle is covered by perineurium. Here's the histology of it. If you look really closely, there's tiny circles here. Each circle is an axon covered by endoneurium. Here you can see a fascicle. This is a fascicle, that's perineurium. It covers the whole thing, that's epineurium. So the nerve would be pretty big. So this is the epineurium covering the whole thing. Let me show you what it looks like in your slides. There's a slide that says mammal peripheral nerve, CS and LS. So So it's a nerve that's in cross section and in longitudinal section. And if you're a person C, this is what you'll be drawing. Alright, so again, we have both cross and longitudinal section on this slide. This is cross section, nice and round. This is longitudinal section, long. So we're going to go to cross section. There are, well, there's 1, 2, 3, 4. There's like one big one and then a few smaller ones. Let's look at the big one. Okay, that's a 4x objective, 100x total. This little dot, that's a single axon. This white part is the myelin, and then the circle that it forms, that's the endoneurium. Tons of axons in this thing, right? You can see the epineurium very clearly, and that's just what's all here on the outside. This slide doesn't show the fascicles that well. We do have slides that show the fascicles better, but let me look a little closer. On this slide, the fascicles aren't very distinct, but you can see it, at least part of it. You see how this tissue starts to go in right here? And how the tissue starts to go in right here? This is a fascicle. So this here in the red, dark red, is perineurium. Endoneurium, perineurium, epineurium. Questions? All right, so those are the different layers, follow the same pattern as muscle fibers, just neurium instead of mesium. We've already seen different types of sensory receptors, so let's focus on just Merkel cells, Meissners, and Pacinians, since those are what we focused on before. So they might appear again. Merkel cells are in which stratum? Stratum basale. Pacinian corpuscles, what layer are they in? Then the dermis, reticular layer. And Meissner's corpuscles, what layer are they in? Meissner corpuscles are in what layer?
Oh, isn't that the
areola layer.
Is that layer, what's it called? Papillary. It's in the papillary layer. I'm not going to test on the others yet, so I'm going to write note myself not to test on that. So Merkel cells, Meissner corpuscles, Pacinian corpuscles, you should know. Slide 34. All of these things that I just mentioned, they communicate, like a Meissner's corpuscle is dendrites with connective tissue, and then this is a pseudounipolar neuron, which then extends to the central nervous system. Same with Pacinian corpuscle, same with what I drew here. A Merkel cell communicates to a pseudounipolar neuron and leads to the central nervous system. I've mentioned muscle spindles, and I do want you to be able to identify them under a microscope. So this is person D, I think. This is a cross section. What we have is longitudinal section. The muscle spindle spindles, they detect stretch of muscle spindles detect stretch of muscles, and if the muscle is too stretched out, then that leads to, if muscles get too stretched out, then we want to contract it. We want to shorten the muscles to protect it. A muscle spindle is an example of what's called a proprioceptor. We just went over the term somatosensation. That's for like touch, temperature, pain. Proprioceptor, that's for body position, tension, muscle length. So a muscle spindle is an example of a proprioceptor, your sense of body position. Proprioception is your sense of body position. There you can see these muscle fibers surrounded by connective tissue. This is the muscle spindle. This is a muscle spindle. So when we look at it under the microscope, though, what we're looking for, it's the same longitudinal view of muscle fiber, and you can see axon terminals over here. But we want to look for a thinner portion where nerve fibers kind of lead to. We're looking for muscle spindles. In a longitudinal view, they're this thinner fiber. What did I note on your tape thing? So person D? C, person C. So the term intrafusal muscle fiber, that's what makes up the fiber within a muscle spindle. It's these fibers in here. They're the ones that help detect the stretch. They're the special type of muscle fiber. They're intrafusal, inside of this connective tissue. So, questions on muscle spindle? Okay. We don't have slides of this next receptor, unfortunately, but I did provide you with a link, so those of you who are drawing it, you can use that link to view it. But this is another example of a proprioceptor. It's called a Golgi tendon organ. It's called a Golgi tendon organ. I know we used that word Golgi before. This is completely different. It's not the Golgi complex like in cells. This is just the same guy's name, but named something else. Golgi tendon organ, as the name implies, it's found in tendons. Muscle spindles detected muscle stretch. Golgi tendon organs detect tendon stretch. If you're stretching your muscles to the point that you're now stretching the tendon, that's probably bad. That means you're really stretching your muscle. If your muscle spindle gets stretched, I'm going back for a second. If you stretch your muscle spindle, you'll tell your muscles to contract and they'll kick out. But if you stretch your Golgi tendon organ, that means it's too much stretch. You'll actually tell your muscles to give out. You'll tell your muscles to inhibit, so you don't overstretch your muscle. It's like if you're trying to lift too heavy a weight, or like someone throws something that's too heavy for you to catch. It's better for you to drop it than to try to catch it, because you'll tear that muscle. You'll damage the tendon. Again, we don't have slides for this, unfortunately, but when you see it in these pictures, here's a longitudinal section of muscle fiber. It's this branch here. You can see the nerve, the dendritic endings here, encapsulated. This is the Golgi tendon. And so since it's the tendon, it's going to be towards the end of these fibers. It's at the end of the muscle. Where's the link? It's, if you go online, I will get to that. I will show you all. Yes. Possibly. I want it to be due Monday, but we'll see. Let's see how much we get done in the next hour. The practice is going to be the same day. This is a good practice for practical, so. Yeah. So, hopefully this reflex idea makes a bit more sense now. You need someone to send something, integrate that information here, whether it's in the brain or spinal cord, and then you send that whatever response out based on what you detected in the first place. Moment. Raise your hand a few more times. Hands on 3. 1, 2, 3. On 3, say the letter. 1, 2, 3. C. If the fascicles and axons are together and intact, we didn't cut through the fascicles, the perineurium is intact, and endoneurium is intact. It's the epi, the one on the very outside. Epineurium is affected. More question? Raise your hand if you need more time. On 3, say the letter. 1, 2, 3. Or hold the letter, hold the letter. I'm sorry, I mixed myself. Hold up your finger, hand. Hold your hand, please. Cool. On 3, say the letter. 1, 2, 3. Great. Sensory neuron dendrites, cell bodies, and axons are found in the peripheral nervous system. They extend their axon terminals into the central nervous system. So cell bodies are out here. Motor neurons, their dendrite cell bodies are in the central nervous system. Their axons and axon terminals extend to the outside. Cool. Any questions? I know we skipped over some slides. Don't worry about them for now. If we don't get to them, they won't be on the test. But here's what we're going to do. I want you to work on your lab checks. So these two groups stay here for now. This table, if you could get lab coats and gloves on, KB, Kelsey, and Isabel are going to show you all the muscles, including the legs. I don't think we covered the leg last time. So we're going to review. Sorry? Yeah. See some dark spots outlining there.
These histologies will be on the practical.
They will be on the practical.
Is there any relation to Purkinje fibers?
Purkinje fibers are in the heart, but they're completely different things. Just like Golgi tendon organs and Golgi complex are different things. Same person, I think. Same scientist. Polish guy.
What is this histology of?
This is of the cerebellum. It's the little brain in the back behind the brainstem.
Sorry, excuse me.
So, okay, here's some good examples. All right. So again, this is like the outer layer of the brain, and you can best see these Purkinje cells, the neurons that are also multipolar. Here's the cell body, cell body, cell body. This mess of stuff, it's just a whole mess of dendrites with glial cells mixed in. So these tiny ones are glial cells. probably astrocytes. But all of this extension is then branches to a whole bunch of dendrites. Let me show you a more clear picture of what it would look like if you could see the whole thing. Here, cell body, dendrites. So if you could parse out one cell, this is what it would look like. Cell body, axons, you can't really see it, but it's there somewhere. And then all of this is dendrites, because it's receiving a ton of information. So back to here. Back to here. Cell body, dendrites. You can't, again, see it very well. Cell body, dendrites are out here. Cell body, dendrites are out here.
Which would you say are the astrocytes?
So you can see how big the neuron cell body is. If it's smaller, it's some kind of glial cell. Since it's mixed in with everything and in the central nervous system, and it's probably not microglia, it's probably astrocyte. Axon, you can't really see the axon. This is the dendrite. Like it's these Purkinje cells are just lots of dendrite. So if it does have an axon, it's overshadowed by everything else.
Okay.
So you can't really make it out.
So we don't have to point that out.
Did I say you had to? If you did, sorry.
What section do you want?
So that's a cerebellum. Cerebrum, cerebellum, we have pyramidal and Purkinje, and they're both similar in that they're both interneurons, they're both multiple. This third one is neurons of the dorsal root ganglion. A dorsal root ganglion, the cell bodies of sensory neurons, like for touch, temperature, and pain, these cell bodies, they all cluster together. So that's what I tried to draw here. These cell bodies all cluster together. That cluster of cell bodies, that's what a ganglion is. The ganglion is a cluster of cell bodies. And because these are pseudo-unipolar, you've got cell bodies off to one side, you've got axons over on the other side. So you can see, when we look at the histology, you should see cell bodies in one area, axons in another area. Get the contrast of. That's good enough. Okay. All of these here, 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 these are all cell bodies of sensory neurons, of pseudo-unipolar neurons. These are all cell bodies. Their axons are going to be off to the side. So all the cell bodies are clustered together. The axons are off to the side. So when you don't see these large round parts anymore, those must be the axons. You see all these cell bodies here. I'm assuming they're myelinated. What kind of, what cells are these nuclei for? Yeah, I'm asking what's myelinating it. Oh, this is the dorsal root ganglion. So, Schwann cells. Schwann cells. It's all clumped together. Let me see if I can find a better. Yeah, so all of this, these are just axons. You can't make out one axon from another, just all clumped together. Dorsal root ganglion, pseudo-unipolar, cell bodies clustered together in one part, axons to another. So you can see all axons here, move over, and now you can see cell bodies starting to cluster together. They're all cell bodies and neurons. Yes? Ependymal cells are the ones that line. Ependymal cells are the ones that line fluid-filled spaces, cerebrospinal fluid-filled spaces. So we have to look for a space. I'm at 40x total. This is fluid-filled space. So all of these cells, those are lining the space, and so those are ependymal cells. We'll get a little closer. There we go. These are ependymal cells. We know we're looking at nervous tissue. If I look down some more, neuron. Neurons are larger than glial cells typically, so I'm trying to find a nice large cell body somewhere, like here. Down on the left, that's the cell body of the neuron. Most of these are glial cells that aren't ependymal cells because they're not surrounded, they're not lining a cavity, lining this fluid-filled space. It's lining the space like here. Ependymal cells here, ependymal cells here. This is the choroid plexus. We'll learn what that is later. But this is what's producing the fluid and circulating the fluid around the central nervous system. So Graham, do you see that? Look for a space. Look for a space. I can come in a minute, but you want to look for an open space. The ependymal cells are this darker one that's lining the space. So look around for a space. I showed peripheral nerve already, I showed multispinal already. Oh, let me go to, I'm going to go up to part A. Neuron, let me show you this. This slide says spinal cord, multipolar motor neurons, nerve tissue. So I'm at 40x total. You can see a bunch of little spots. Those are nuclei, but of different cells, not necessarily neurons. Remember, neurons generally have larger cell bodies. This is a smear, so this is like nervous tissue that's been spread out. We're looking at motor neurons because that's what the slide says. And we can see how it's multipolar. Here's the cell body of the motor neuron. All these other things, they're glial cells because they're much smaller. We'll get to what they are in a second. Here is our motor neuron, and we can see all these extensions. The extensions, we know that this extension here is an axon. If we follow it along, we can see all these nuclei that are running along that extension. This is a motor neuron. We see nuclei running along the extension. What kind of glial cell is running along the axon? It's a motor neuron. What? What's the glial cell made? It creates the myelin, the motor cells. Schwann cells. Schwann cells. Remember, motor neurons, their axon extends into the peripheral nervous system. And if you have a peripheral axon that's myelinated, it's covered by Schwann cells. So these are these are cell bodies running along that axon of a motor neuron.